we'll get started here. So today it's a pleasure to have Sebastian Dorn, who's visiting us from MPA, Max Planck Institute for Astrophysics in Munich. He's passing through his way back from the IAU, and today he's going to tell us about all-sky reconstructions of the scalar potential.
Yeah, thank you for the introduction, and thanks for the opportunity to present a part of my work here. So, yeah, as mentioned, I will talk about the reconstruction of the primordial scalar potential. This is a work actually, or in particular, done with Maxime Greiner and Thorsten Enslin. They're also both from the Max Planck Institute. And maybe we just start by considering that we want to infer early universe signals from data. So that could be, for example, the primordial scalar potential itself, or its statistics, so the primordial power spectrum, or you want to, for example, learn about something non-Gaussianity, so directly from inflation or other early universe signals. So many of them are actually imprinted in the curvature perturbations, or the primordial scalar potential. And the primordial scalar potential is transferred via the radiation transfer function to the CMB at the distance at the less scattering surface. And then, of course, we have a few effects, like, for example, the ISW effect or the Sonia-Vcelevic effect, which affects the CMB before we can observe the actual CMB today. And what people usually do if they want to infer early universe signals, they have to solve the whole inverse problem here, going from the left side to the right side, which might be expensive, or is actually be expensive in many situations. So we just ask ourselves, if the curvature perturbations already informed about that stuff, why don't we just reconstruct these curvature perturbations, or in that case the primordial scalar potential, once from data, and then do the inference starting with that data set. And that's more or less the motivation for that work. So if we want to do that, we have to agree on a data model, and we parameterized here the CMB data at a linear response operator acting on the primordial scalar potential phi. This response operator in particular incorporates all the physics, so the linear transfer functions, as well as an observational mask and the instrument beam. And we have additive noise, so statistics for noise and for the potential are assumed to be Gaussian. So the potential itself is a three-dimensional quantity. That means the really naive answer to just get an estimate for that potential would be to apply a Wiener filter operation. A Wiener filter operation, I will, in a few slides, I will talk about it a bit more detailed. It's nothing else than like a matrix or a linear operator acting on the data. And it's known to be optimal. And with optimal, I mean with respect to the L2 error norm. So that's a well-known thing. And that seems pretty easy. However, there's a problem if we consider the amount of pixels involved. So the CMB data set is pretty large. So with 10 to the 7 pixels roughly, the potential, however, is a three-dimensional quantity. So we have we have the CMB pixels to the 1.5, and the response acting on that potential is then data cubed, which is really a huge amount of pixels. So applying R to phi is not really a problem. You can do that. But the Wiener filter, in particular, involves an inverse operation of such an operator. And you have no explicit form of that operator. So you have to apply here, in that operation, for example, a conjugate gradient method to get the inverse operation. And that is very expensive if you have such a number of pixels involved. So it's just not doable, or if then at least very expensive. So, or just consider we have the reconstruction, which is very, very expensive, but we want to calculate the uncertainty map for that. That's not doable. So one way to solve this problem is actually to look at that picture. So imagine here we are the observers at the center of the picture, and the boundary is given by the distance to the last scattering surface. And instead of reconstructing the primordial potential in one go, we can reconstruct it slice by slice, which makes the problem easier because the operator is just going from a CMB data set, so from one sphere to another sphere. And this idea is actually not new. It was first mentioned by Yadav and Wandelt in a paper of 2005. And that means we have to write the data in a bit, in another form. So the scalar potential phi is here now living on the sphere. So these are ALMs, but they depend on the distance or on the radius between us and the last scattering surface. Then, of course, you have to integrate over the radius. So to sum up all spheres, you have to take into account Bessel functions. These actually getting into these equations do a projection from the three-dimensional potential onto a sphere. And then you have finally doing a convolution over the transfer functions. So here we consider temperature data only, so that's the reason why we have only temperature data here. So this is the whole physical part. And then we have to include an instrumental beam for a satellite, and we have an observational mask, which masks out the foregrounds, basically. Okay, but still, this is a linear operation acting on that potential, now on the sphere. And we have, again, Gaussian noise on the sphere. So yeah, so linear operation means we can, again, use a Wiener filter. So let me quickly explain what a Wiener filter is doing. So as I said, we have a linear data model. That's crucial for a Wiener filter. We have, we are interested in a posterior probability distribution, because we want to get an estimate. That's, for example, the maximum of the posterior. This posterior probability, so it's the probability of the scalar potential given the data, can be expressed by Bayes' theorem. So it's nothing else but the likelihood times the prior, so our prior knowledge about the statistics of phi. This is, for example, the primordial power spectrum. And it's just normalized by the evidence. So if we want now an estimate for phi, we can just taking the phase space integral over phi and the posterior probability, which gives us an estimate. And now comes the crucial point. If we assume, or if you can assume that the statistics for phi and the noise is Gaussian, then we can, doing this phase space integration analytically, and ending up with just one operator acting on the data. And yeah, I haven't written that operator out because it's a bit lengthy. It's just one matrix actually. But the requirements is linear data model and Gaussian statistics. Okay. So how do we get one slice or one sphere between us and the distance to the last scattering surface? So we actually have here the Wiener filter solution of the three-dimensional problem and project this solution onto one sphere with that T operation. So that should be the estimator on one sphere for the primordial scalar potential. So you can work that out. There's a lot of lengthy equations. And basically, you end up with that estimator, which is nothing else but the data, so CMB data, weighted by the data covariance. Then you have a bit involved operation R2, adjoint. This operation is just a response operator in 2D, so it connects the data of the CMB to one sphere at a specific distance. It actually projects back the weighted data from data space into the space of the primordial scalar potential. And then finally, you have to convolve it with the primordial scalar potential to get the estimate. And again, R2 includes all the physics. So you have here the transfer functions, you have the beam and a mask. Okay, so this is for temperature only. You can extend that to polarization. If you do that for polarization, you have just a vector of data. You have temperature and the Stokes parameter Q and U for polarization, but it's still a linear operator R acting on phi and additive noise. The R operator now looks a bit different. Yeah, it's this guy, and this RT and RE are actually that known equation from a few slides before. So we have here just T or E, depending on if we're working with temperature or with E mode polarization. It's not coupled to the B mode because it's the scalar potential. Then we have a transformation from the T and E, which are the theoretical equation, to the observational quantities, so to T, Q, and U. Then we have to include the beam, as before, and the observational mask. Of course, that depends on if we have temperature data or polarization data. You have to choose different masks. Yeah, so that's basically it. You can just use the same Wiener filter, just applying or just involving another response. Okay, so what are the achievements of this approach? So one obvious thing is we have now a really full polarization of the 3D Wiener filter equation, because you can solve for every sphere independently. Yeah, you don't have to do that in one go, but just solve for one sphere on one core and another core for another sphere. That makes the approach very fast and cheap. We can include polarization data, that's not a big deal, and we can now sample uncertainty maps. And we can do that because the operator is acting from a two-dimensional quantity to a two-dimensional quantity, so it's not really big, and we are able to do that numerically. Okay, and here you see some results reconstructed from the WMAP temperature data, the 9-year WMAP temperature data, in particular the V-band. I have to say that I only used temperature data here because I did the whole thing with polarization, but it turns out that the WMAP polarization data was just too poor to add any information. And Planck data wasn't published at that moment. So you see here a reconstruction at a distance of 1.01 times the distance to the last scattering surface. So this is the scalar potential. You see these masking effects in the galactic plane. You see, or what you maybe see, it depends probably how near you are to that, is that the result looks a bit grumpy. That's actually because we only use temperature data. That means you have L blind spots in your response or in your reconstruction. And you only get rid of these L blind spots in your reconstruction. These are caused by the transfer functions if you include polarization, because polarization and temperature data are out of phase, or these transfer functions are out of phase. That's the reason why it looks a bit grumpy. And you can do that for distances a bit before. Here you see that it even looks more grumpy because the L-blind spots move to larger scales. And you see also that we lost a lot of small scale information. So if we go away from the last scattering surface, we are only able to reconstruct really large scales, which is also reasonable because, I mean, we have 2D information and cannot perfectly reconstruct a three-dimensional quantity. And of course, you can go a bit beyond. And here you see the same effects, only larger scales, but it looks now more smooth. And the reason for that is that the L-blind spots move to higher L. Yeah, and as said before, we can sample uncertainties. So, yeah?
So how does it compare with the actual WMAP image, I'm wondering? Because I thought on large scales where we're just looking at the Sachs-Wolf regime, we're basically mapping out the phi fluctuations that sort of the last scattering, right?
Yeah.
So are you able to push into smaller scales where the mapping is more non-trivial than just the simple redshifting out of the potential?
Yeah, right.
You know what I mean? So I'm just wondering what it looks like compared to just the simple, to the actual data, data.
Yeah, if you go away from the Laskerian surface, it's basically nothing else than the Sachs-Wolf effect. If you go far away, it's just the large scales. But if you do that at the Laskerian surface, we have really the small scale information. That's something new. That's not just the Sachs-Wolf effect.
Right. So you're saying there's some information in here that at smaller scales than where the Sachs-Wolf effect dominates. Like you're going into the acoustic peak regime of the CME.
Not completely sure what you mean.
Because up to L of 100 or so, we're mainly just looking at the CME photons redshifting and blue-shifting out of the potential wells. So on large scales, this map should look the same as the CME, as the WNet map, I think. Right?
Yeah, times minus 1/3 or something, right? Yeah.
But then, so on large scales, it should look the same, but then on smaller scales, you're seeing something new
yeah.
in the map. Is that right?
Yeah.
Okay.
Yeah. Okay. If we want to calculate the uncertainty, that's also well known how to do it in the Wiener filter theory. So we have this Wiener filter operation acting on the data. You can now just place out the inverse noise covariance and a joint response operator from the Wiener filter operation. You end up with, or you then have a new operator, which I call D. And you can show that the 1 sigma uncertainty of the reconstruction is just given by the square root of the diagonal of that operator. So it means you have to sample the diagonal of a matrix once, and then you have the uncertainty. And here is, for example, the uncertainty map at the distance of the map I shown before, which is clearly dominated, of course, by regions where the mask is, and is getting minimal well outside of the mask.
So it's a tiny range, isn't it?
Yeah, it is a tiny range. It's not really, so it's just that we don't get too much information with that temperature data. It's unfortunately it's not too much in it, yeah. Okay, so now we have a reconstruction, and then we can, of course, do something with that. For example, calculating the primordial power spectrum, and this is, for example, done here. It's, however, done for one sphere, because here we have the most information, and for temperature data only. You see here the blue curve is a theoretical power spectrum, and green and red lines are inferred power spectrum. The red line is in particular produced by enforcing smoothness. Yeah, you basically see that we follow the theoretical power spectrum over roughly 1 order of magnitude. On large scales, of course, we have cosmic variance, and on small scales, we are affected by subhorizon physics and noise dominance. And I have to say that this reconstruction of the power spectrum is rather a consistency check of the algorithm, because there are a few things, or there are a few issues which we neglect here. And the first point is that we use for our reconstruction, because we are doing a Bayesian reconstruction with Bayesian stuff, we had a prior assumption for the statistics of phi, which is the primordial power spectrum. So that means if we then infer the power spectrum, that result might be biased. However, the temperature data is pretty powerful, so that means that the result is probably not strongly biased, but it is a possibility. The next point is I haven't included the uncertainty of the reconstruction in my power spectrum inference. So I haven't took the whole information. Then I need, of course, polarization data to compensate for the L-blind spots. Just imagine we want to figure out if there are some wiggles or something in the power spectrum. So if I have L-blind spot in my response, this could cause such wiggles which are not real. Okay, sorry. The transfer, the lin. Yeah. If I say L-blind spots, then I mean that the transfer function have some regions where there are just 0 for temperature data, the linear transfer functions. And in these areas, I have no information in my response. Because it's just...
You mean in L distance space, is that what you mean? By a blind spot?
No, I mean actually on the sphere, the LMs, ALMs, and the Ls. So I mean this L.
No, he's saying that it's a T only, right?
Or polarization, doesn't matter.
Well,
No.
But if you combine them, you get rid of them.
Yeah, right.
no, that's not true though. That's just,
Why is it not true?
well, Shiji and I, in my view, could nail this problem, right? For zeta reconstruction, so we made all of these maps, we didn't understand them extremely well. It is true that the ability to reconstruct has an L dependence because of the structure of the transfer function or the correlation function. The polarization is just adding a slightly different direction. I mean, the problem here is that for each LM, you're only getting one mode for T's and one mode for E's. And so you can't reconstruct in depth very well. So the question is, what are you reconstructing? And so there are regions that you don't have a hope of doing any reconstruction on. And so what I don't understand here is what your definition of L-blind spot is.
Yeah. So we have here, this is the response operator, RTE. And L-blind spots are defined just by the fact that this GL equals 0 for that specific L range or for that specific L value.
Okay, so yes, you are using depth. Yeah, right, no, exactly. There are vast regions.
Yeah, right.
Terra incognita that is impossible to be probed.
Right, and it,
That's what you mean.
yeah.
It's really an L-blind spot.
What do you mean by depth?
What?
What do you mean when you say you
Well,
depth?
I don't know if you remember any of the pictures that we show on this, but if you plot effectively, yeah. So we work in showing L-pi space, and so there's this huge region, obviously, in between the distance of last scattering and reionization, where there's no information.
Yeah, yeah.
So it's got 0 probe.
So what,
Then as you come down, as the reionization starts to get lost, you then end up with a little bit of ISW coming in response. So those are the regions, and obviously we will never get probes in the in-between region, unfortunately, so we can do no reconstruction at all between the last scattering surface and the onset of reionization.
yeah.
And then what we get with reionization is extremely low L. It's not very much information. And similarly for ISW. So, that's just the limitation of the fact.
Yeah.
The way the universe is.
Definitely. So we are able to reconstruct basically a thin shell around the less scattering surface. So that's where the information is. Then, of course, you can't go to very high distances away from the less scattering surface. But it is actually true that the transfer function for the temperature is 0. The transfer function for the E-mode polarization is not 0 because they're out of phase.
Well, there's still huge regions where there is no probe. I mean, obviously, polarization is not probing the region between combination and reionization.
No, of course. But for example, at the last scattering surface.
projected.
Yeah.
So because of that fact, I mean, they are correlated, so that component doesn't give you anything more. It's the uncorrelated.
Yeah, but for a fixed distance, for example, the distance to a scattering surface, this adds new information for these L-blind spots. That's what I wanted to say. Okay. Yeah, the primordial power spectrum. Okay. Yeah, and of course, we have to include not just the single sphere, but also the information we get in this thin sphere around the scattering surface. So this all should be taken into account if you want to reconstruct that power spectrum probably. And here's, for example, one proposal how you can do that. So we're actually starting here with a power spectrum assumption in our algorithm. So that's, for example, the primordial power spectrum, the theoretical one. We do a Wiener filter operation, getting back the reconstruction as well as its uncertainty. Then we do a Bayesian reconstruction of the power spectrum, including uncertainty, and then using this new power spectrum for the next initial guess for the Wiener filter and iterate that procedure. So it's actual. Sorry? The uncertainty from the mask? Well, that's all. So that's all included in principle. Sorry, can you speak up a bit?
So there's three kinds of uncertainty. First of all, the map and also sky is
right?
the map and the noise.
Yeah. So.
And the last thing is that the projection, so you have measure the parts of the fluctuation.
That's all right, but that's all naturally incorporated in the Wiener filter. So if you do that in a fully Bayesian framework, you take that all into account. So for example, in regions where you have high noise, the Wiener filter automatically downweights that and puts more uncertainty there. So you should see that all in your uncertainty map. Sorry?
So you don't know anything. So I wasn't surprised.
Yeah, you don't, of course, know anything of the regions under the mask. That's true, but you know something about the correlation structure. So you know about the large-scale correlations. So the Wiener filter is able to propagate your signal on large scales into masked regions. That's actual Bayesian inference.
But that means that you know the masked fixed correlation function inverse, which is, of course, super challenging. Essentially, nobody knows how to do that. So you made an approximation to go after. There's no way anybody can do that for Planck times because of the sheer number of pixels. So
why should I? Sorry, let's go back to that. Okay, here.
No. He's trying to do short distance as well.
Yeah, but what should I know to do that calculation? The inverse of the? And inverse. Yeah.
Do I understand what your D is? D is the pixel information, or is it?
Yeah, right. It's the.
So what exactly is N inverse?
N inverse is the noise covariance inverse. Yeah. Well, the Planck delivers a noise model, right? As well as WMAP. So I can implement the noise covariance.
Why isn't it C total inverse? Which is the usual Wiener filter.
Because that's actually okay. That's actually the Wiener filter written in the data domain. In the data domain. So you can apply a Wiener filter, or you can write down a Wiener filter in the signal space. So in the space where the potential lives, or you can write it down in the space where the data lives. And if you write it down in the space where the data lives, then you get here this usual C. But that's the signal space version of the Wiener filter.
How are you damping that cosmic current?
I mean, that's okay. I should have written D out. So a lot of these prior informations are all incorporated in D. So D is R deca inverse R plus the correlation matrix for the potential. And that inverse. So there is a weighting inside D.
It looks like if you have zero noise, you can have
Yeah, but you never have zero noise, right?
just eventually perfectly measured zero noise.
Yeah, of course, if you have zero noise, then you can get into problems.
Well, with zero noise, you do get reconstruction. Get better reconstruction.
Yeah, of course, then probably you don't use the Wiener filter equation for that.
That's why I think
I don't know, I haven't thought about the case where you have zero noise. But I mean, we can talk about that operator and how it looks, and I can transform it easy to the usual Wiener filter with that C propagator just after the talk, if you are interested, and how it's done exactly. Okay, so for that slide, I just want to mention that a full Bayesian framework to do that has been worked out and explained in a paper of Niels in 2011. Okay, so the next thing we are planning to do is, of course, using now the Planck polarization data, maybe or probably in collaboration with the Planck collaboration. We want to do crest checks with large-scale structure reconstructions, for example, from Jens Jasche or Kitora, which also reconstructed the initial conditions, but from large-scale structure. We want to do some symmetry investigations of the reconstruction, and as motivated at the beginning of the talk, we want maybe to infer some inflationary parameters or recombinational parameters from the data, or from the reconstruction. And here I want to present just a little simple example how that could look like. And I want to show you how we can reconstruct an inflationary parameter by local non-Gaussianity. So here again, the first slide, you see here, yeah, that's a sketch where Gaussian fluctuations are produced during inflation. Just for simplicity, we have here two inflatons. They couple somehow, producing non-Gaussianity, and these non-Gaussianity should be imprinted then in the curvature perturbations, which means I can write down the potential as a Gaussian component plus some non-Gaussian components, including these parameters. Okay, then let us just assume further we take the simplest curvaton model with an inflaton and a curvaton, and in that model one can show that FNL and GNL can be written in terms of such a curvaton parameter, which is defined here. So it's basically the density of the radiation divided by the density of the curvaton. But it's not really important at the moment, just that FNL and GNL can be expressed in terms of these curvature parameter. So here you see, for example, possible values of FNL and GNL. The red dashed curve are the Planck constraints on FNL. We have the dotted line. These are 0 FNL, 0 GNL. In blue, you actually see the possible values of the curvaton, simplest curvaton model in that plane. And if we also take into account Planck isocurvature constraints, we are inside that red square here. Okay, so that means if we want to infer, for example, the kappa, so the curvaton parameter directly from our scalar potential reconstruction, we again have to first formulate the posterior for that. That means, because FNL and GNL would depend on that, we can first formulate a posterior for FNL and GNL. So this is actually a pretty lengthy derivation, which I will skip. The result is shown here. Means the posterior for FNL and GNL, given the data, depends on a prior, of course, for FNL and GNL. For example, the Planck constraints. We have some e to the minus, and then h is just an analytical function. That's all you have to know, depending on data and the Gaussian reconstruction of the scalar potential, given FNL and GNL. So this part is actually the easy part, and then you have this nasty guy, and this is actually a determinant of a matrix. And this matrix involves, unfortunately, FNL and GNL, which can lead to the fact that this probability, this posterior distribution gets some non-Gaussian part, so it's getting skewed. That means you actually have to calculate a determinant, and this is always not really easy. I will come to that. So what you see here is, for example, just a mock data simulation of the curvature perturbations from a kappa parameter equals 5 originally. So we produced the scalar potential and then applied our formula to get the posterior for this kappa parameter. You easily get that if you replace FNL and GNL by their kappa expressions. And here's, so we let out the prior, so it's just the likelihood, but you see that we could find this initial value of kappa equals 5 pretty good. Okay, that's just an example what can we do with that. And maybe I should spend now a few words on that determinant calculation.
Do most of the constraints on kappa come actually from the FNL?
Sorry?
Oh, so kappa determines both FNL and GNL, right?
Yeah, right.
But the constraints on GNL is much weaker than FNL, so does this constraint mostly come from the FNL? Or?
Yeah, so what you see here is just the likelihood without prior assumptions. So these stuff should be all included and in your prior if you do it with real data, and then of course this changes. Yeah, but you're right. And this is, of course, you can do it in another way. It's just a mapping of the non-Gaussianity parameters into the area of inflationary parameters for a given model. Okay, I don't know if any of you is really affected by that problem, but I know a lot of guys at MPA which are dealing with Bayesian estimators, and often they have problems with the determinant calculations, because it's not really known how to do that for large operators. So the first thing is, if you have a matrix, let's call it A, and you want to calculate the determinant, one way how you can do this is starting to split it up into a diagonal part and a non-diagonal part. The diagonal part can be just sampled, so that's doable. Then you have these splitting. And so this delta is the determinant, the logarithm of the determinant. So that's d plus n. And what you then are doing is just replacing the logarithm of the determinant by the trace of the logarithm. And you place out d, and actually then doing a Taylor expansion of the logarithm and ending up with that formula. So that formula is pretty good because it's cheap. You just have to sample the trace. That's not more expensive than sample a diagonal. However, you can just use it if n d inverse is much smaller than 1 spectrally. And this is unfortunately not often the case, or not. There are cases which this is not guaranteed. And there is a little trick to solve this problem. You can actually just insert here a little parameter, t. And if t is really small, irrespective how large n is, then you can actually use the Taylor approximation. And so in the following, I will just focus on matrices which are positive. So, for example, covariance matrices, which are usually play a role in Bayesian inference. So the little trick how to solve this problem is just to building the derivative and integrating it again. Okay, that sounds easy. Just taking the derivative with respect to this parameter, that's actually that formula, plus a boundary, and that's your final formula to calculate determinant. Now you probably wonder, I mean, how is this is this cheaper than anything else? So it's actually cheaper than just using, for example, a sampling of an explicit, to explicify basically that matrix by, for example, sampling with unit vectors. That's extremely expensive. You can't do it for operators acting, for example, on CMB data. Another thing is, okay, you have here the trace. You have to calculate the trace for every integration step. Sounds very expensive. And you have here an inverse, which is also not cheap. However, the great upside of that formula is that you don't have to use many samples for the trace probing here, because afterwards you integrate that and errors get averaged. So, for example, so this is the integrand. So here in black you see the exact value, and in in dashed you see that sampled solution, and here's this parameter t. And you see that the errors are pretty large because we used, for example, so this is just an example of a non-diagonal matrix. And we just, for this trace probing, we just used 8 samples. So usually you need 100 or 150 minimum. So errors are pretty large, as you see here, but due to this integration, they just cancel each other from time to time. So on average, you need a very low number of samples for doing that. And that makes this approach, yeah, I would say nice.
Because you need the inverse.
Yeah, of course, you need the inverse. That's expensive.
On the side of the matrix.
Yeah, of course. You have to apply, for example, again, a conjugate gradient method, which is expensive.
So do you have a trick for that?
You can, well, there is a trick for that. You can, for example, solving the conjugate gradient once, and then using, for example, that result for initial guess in the conjugate gradient for the next time step. You can do that, for example. So that really makes the conjugate gradient in just, you have to solve it for one step, and for the other steps it's pretty fast. However, then you can get, or your errors for that trace can get biased. Because you are always using the same initial guess means that your errors are maybe not distributed so randomly, but maybe all, for example, positive, and then you need more samples on the other side. So that depends on your problem. But as far as I know, that's one of, or I'm not aware of other method which can sample the determinant, actually. So that's one way how you can do that with that formula. I mean, calculating a determinant is expensive in any way. Yeah, so as I said before, achievements, few samples, and you can actually, of course, for every time step, if you don't use the same initial conditions for the conjugate gradient, you can, of course, do that fully parallelized. So if you have enough computing power, that's maybe a way. Yeah, and that's actually it. Thanks.
All right, any more questions for Sebastian?
So regarding Planck 2015, you're working with Torsten on this, right?
Yeah.
Yeah, you should know all about this. So the original plan that we worked on for a long time was to do a huge number of matrix conversions by French supercomputers in order to get these primordial reconstructions, not phi, but zeta.
Okay.
Which is what Chi-Chi and I have worked on. And then they found, so they were done, it absorbed a huge amount of computer time, and then they found a bug. So then the question was, we were going to do it all over again. The idea was that, and this is sort of obvious, that this was going to be the way to improve the FNL estimates. So it was going to be the new method that was injected into the Planck 2015 non-Gaussianity paper. And then we ended up going with conventional methods, which was too bad because we thought our stuff was going to go into that non-Gaussianity paper, which was the zeta reconstruction. So, so just as a point, there is a very active Planck community that has been doing primordial power spectrum primordial
I know.
map reconstructions.
Mm-hmm.
We tried to get our stacked zeta maps, which are better because the fluctuations are smaller, into the isotropy statistics paper. But for one reason or another, they went with their polarization maps and anisotropic maps, but they didn't want to stick in this, so we were going to have to do something separate from that. So it's unfortunate. There would have been a whole volume of stuff on zeta reconstruction, and the gods is more willing for Planck.
Yeah, at the IAU in Hawaii, I talked together with Torsten with Jean-Luc Pichet about that, about Jean-Luc Pichet, the PI, and he seemed to be very interested in that stuff. So maybe just we can talk afterwards. Yeah.
So I just had a question about the primordial power spectrum.
Sorry.
The primordial power spectrum reconstruction that you showed. So you need to assume something as a prior when you start.
Yeah.
Which is basically that power spectrum. So what happens? Is it possible to relax that prior at all and still get meaningful?
Yeah, so I checked it with a few other priors. So just with tilted power spectrum or something, it changed nothing. So the temperature data seems to be pretty powerful in respect to that power spectrum.
But you need to assume the primordial fluctuations are a Gaussian random field with some power spectrum.
Yeah, that's the assumption here in that reconstruction. It's actually a good question. So maybe you can relax that, but I mean, you can get into conflict with your Wiener filter. So you maybe then should use another method, which is probably more expensive. So let me quickly go back. So for example, in that reconstruction, you see here that scalar potential, but it's the Gaussian one. So you actually have to find a way to reconstruct not this quantity, but this from CMB data. Okay?
But that's what they do in all of the non-Gaussianity work.
Yeah, exactly. But yeah, you can do that with a KSW estimator, for example, for FNL. That's actually using that Gaussian field. Yeah.
So the reason that we don't use, so the formula is a pretty interesting one for the power spectrum reconstruction. It's got a lot of similarities to quadratic reconstruction, the maximum likelihood results. got one extra filter that appears in it. But the problem is that reconstruction method does not include a lensing correction.
Yep.
And so that's why doing power spectrum reconstruction in a quadratic way using the high likelihood code is a preferred method, and that's why
Yeah.
we put in the inflation thing.
Yeah.
So the same thing goes, unfortunately, in we use white bullet, but all of these early universe reconstructions are not accurate. They have not had lensing data.
Yeah.
And so that means that there is a residual complication, which is why one isn't really wanting to use them for science very much. They're interesting, they're instructive. We thought they were great visuals for science.
Yeah, that's completely right. And actually, a colleague of mine at MPA, she works on a delancing operator, and I know that Ben Wandel also works on that. There were a paper, I think, this year or ending of last year, presenting such a method paper for a delancing operator. And so that's, of course, dream that we can incorporate that lensing operator here in that response operator, which then does delancing and reconstruction once. But of course, I mean, that stands on my plan, but it's not doable at the moment. You're completely right.
Yeah, I think we have a little bit of distance to go before we're effectively delancing. Maybe you just read out.
We should be pretty
The
close.
decision was made in Planck not to try to de-lens on 2015 data.
So the lensing reconstruction isn't good enough for it, but this other tracers can be, right? The CIV maps can be used to de-lens, for example.
But it wasn't that it escaped the notice of Hansen and others that it would be a good idea. It's just that the noise turned out to be too large for it to be an effective reconstruction.
Yeah. Right.
And so, there will be a future in which we could, maybe the final Planck data will be better for this when we nail all of the polarization.
Right. Yeah, that lensing map is still pretty noisy.
Yeah.
But the
So that's-
CIV should work though, right? The CIV is 80% the same field as the lensing field, and we know it, the sample variance over much of the spectrum.
All right. Maybe we should wrap up there. There should be cookies upstairs, and let's thank Sebastian again.